Moving on to chapter 4, here's our objectives. Take a look at them on your notes. We've got some vocab to take care of. Vocabulary here are these things, and I want to be on the same page with vocab, and I want to talk to you about how AP uses that vocab and little twists on the things they can do to not really intentionally trick you, but just be really purposeful about making sure you know and understand those things. We're going to talk about the extreme value theorem and the local extreme point theorem. You have an outline of vocab terms and theorems. We won't really explicitly deal with that today, but I think that can be a good study tool down the road working at chapter 4. So again, keep in mind, we're still working with derivatives, so we're not going to be doing a lot of things that are crazy different than what we did before. A big part of chapter 4 is looking at graphs and understanding specifics about graphical behavior using calculus. So you found maxes and mins in pre-calc, you found vertex points in higher algebra, but we're going to take away your graphing calculator and we're going to be able to do things using calculus and our brains. Won't that be fun? All right, we can't forget what we know about functions, but we're going to have to defend what we do using calculus. So consider this is f of x, and f of x is a basic function with a dot on this end and a dot on this end and some cool behavior in between. So I'd like to define some of those vocab terms using this graph, and you tell me if it makes sense here in just a minute. So the first one is absolute or global extrema. Okay, extrema is a general word for extreme values, maximums or minimums. And I think you had some exposure to that in pre-calculus. So where might the absolute maximum be on this function? Right around here, 2 and 2.5, right? That point right there we would refer to as an absolute max. Okay? Now, just so we're clear, the AP with capital T, I guess. AP will sometimes just call this the maximum value. They won't say absolute max. They'll say, what is the maximum value of the function? And maximum value implies that you're trying to find the biggest. And that is the largest value of the function on that interval. We can agree on that? How do I know it's the largest on the whole interval? It's kind of a duh question. How do I know it's the biggest? Because you can see it. It's bigger than all the others, right? Okay? Later on this hour, I'm going to take that picture away from you. Okay? What is the absolute min? Where is it? It's way over here on the right. This is the absolute minimum, or the minimum value of the function. Okay? How do I know it's the absolute min? Because it's smaller than all the other points on the function. You can see it. You look at it. It's lower than all the other values on the function. Okay? What might we call that point? Look at the vocab list. Okay, we could call it a local extrema. We need to be more specific, though. This is a local minimum. How do I know it's a local minimum? And what makes the word local apply here? What does local mean? In the small area, in its neighborhood. I like to use the word neighborhood. Neighborhood makes me feel like I'm part of something important. I live in a neighborhood. In its neighborhood, it's the smallest. And when I say the neighborhood, it's like that neighborhood. Okay? It's not the smallest value on the whole function, clearly, but in its neighborhood, it's the smallest. So it's a min point, but it's a local min point. So then using that idea, what would we call this one? That's a local max. Okay? There's one more. I'm going to use this one. That one right there, the end point, is also a local min. Its neighborhood is a lot more limited. It's like on the edge of the neighborhood. And its neighborhood is only the points to the right of it. But it is the smallest. Okay? Good so far. Does that help bring some clarity to the vocab? Okay? Extreme values, just in general, Peaks and valleys. I mean, I think that's one way. I mean, it's not a formal definition. You can think of them as peaks as valleys. You could think of them as local maxes and mins. Okay. So I think we've already answered all of this. I think you can go ahead and read through it, but I think we've already kind of answered that, and I don't think we need to rehash it any more than that. Is there an absolute max? Yes, there is. We identified it. We looked at the picture, and we found the biggest. We looked at the picture, we found the smallest. Okay? Good so far? Not a lot of crazy new vocab there, I don't think, but really important. Okay? Just refining our understanding, using a little bit of notation. These are not new questions, and I'm going to kind of help you with it. I'm not going to leave it open-ended for you. Define the following. A maximum value. What word is missing? It doesn't say absolute, and it doesn't say local. If they say neither, and it says maximum value, it's implying the absolute max. Okay? So if there is a maximum value at some x value equal to c, we can state that f of c is greater than or equal to f of x for all x. That's mathematical notation for saying the y value at x equals c is bigger than all the other y values. Does that make sense? If we had a graph to look at, how would we know it's the biggest? I kind of already asked this question. If we had a graph to look at, how would we know it's the biggest? You can see it. It's the highest point, right? Okay. It's bigger than all the others. Duh, you can see it. But if you don't have a graph, we need another method. We'll get to that before we're done today. Similarly, a minimum value occurs if f of c is less than or equal to all f of x for all x. Why do I put the or equal to there? You could have multiples. Okay? But the other thing, too, is that c is an x value. So its own x value can't be bigger than itself. It's got to be equal to itself. So that's another way of looking at it. Okay? An extreme value, really it's just, again, an extreme value is any maximum or minimum value in the function. Good so far? All right, moving right along. Will you slow me down if we're going too fast? Okay. Another little graph. Got lots of different ways of rehashing this same idea. So if it feels like I'm overdoing this or repeating myself, I think there's some things that are really important. Okay. So definition of local max and local min. You can write your own definition if you'd like, but I would say that in their neighborhood, they are the biggest or smallest, I guess you would say, for mins, right? Smallest for mins values. Okay? Really, why do we distinguish between local maxes and absolute maxes? Because polynomial functions that are really cool might end up having multiple maxes and mins. There's a cool polynomial function that has a local max and an absolute max. Cool? Also has a local min. Good so far? Question? Yes. The question is, would this absolute max could it also be qualified as a local max? Yes. And we're going to talk about how we distinguish those in a specific example. But yes, you would also refer to this as a local max. But since the phrase absolute max is kind of more powerful, it's got more gusto to it, you would normally just refer to this as the absolute max. You wouldn't be wrong if you called it the local max. But again, AP will say, find the maximum value of the function. If they said find the maximum value of the function, they want that one, not that one. Does that make sense? Okay, good question. Good clarification. Okay. So then, I don't know if we need to write, I don't know if I need to write anything for this. What's the difference between local max and absolute max? You're kind of developing a little bit of understanding here. Local means in the neighborhood. Absolute means there's no other value that's bigger, right? Local. I mean, it's a peak or a valley on the function in some ways. Okay, absolute max. There is no point bigger or smaller, depending on which word you're using. Okay. I don't know if this helps. I'm going to add a phrase here. On entire interval or domain, depending on what we're looking at. We're going to talk about the difference between those two in just a minute. Okay? I want to get to the good stuff, but I want to make sure we're clear on vocab. Okay? Will you now, I want you to look at this question, and I want you to open your textbook to page 248. There are 6 pictures, and I want you to look at the pictures, and I want you to look at the words inside the boxes. And I want you to just try to kind of wrap your mind around whatever you can wrap your mind around and defend what they're saying and ask yourself the question, why? Why does this one have a max? Why does this one not have a max? Why does this one have a min? Why does this one not have a min? Why does this one have neither? Why does this one have both? So I want you to take about a minute and a half and just look through and try to digest page 248 because I think you can do a lot of it on your own. I'm going to pause the recording here and then we'll come back together. Okay, taking a look at those top 4. Okay. Very first graph, we have an absolute min. Everybody okay with that one? Okay, everybody's okay with that? How do we know it's an absolute min? Because we look at the graph, it's a parabola, we know there's nothing smaller. Duh, right, we okay with that? Why is there no absolute max? Because it keeps going forever. It's on an infinite domain, right? Goes from negative infinity to infinity. So no matter how far I go to the left and right, the function's always going to get bigger. Now, it changes a little bit when we get to this second example. Why is there, we're good with the absolute min. Same idea, right? Why is there all of a sudden an absolute max? We stopped the graph. We took an interval. There's an interval there that we care about. We've limited the interval. So if I just look at the graph on that interval, that is the biggest. Nothing bigger. Good? Okay, bottom left. All of a sudden, we've now changed it so that it has a max for the reasons stated above up there, but why does it have no absolute min? There's a hole there. There's no defined point. It keeps going closer and closer to 0. We could say that the limit as x approaches 0 is 0, but you don't need to worry about limits in this place. The idea should still be kind of hanging out in your mind that it's approaching a minimum value of 0. The important thing in here is that it never actually gets there. There's no minimum value because 0.000001 will have another value that's closer to 0 and lower and closer to the x-axis. Does that make sense? Okay. The key phrase here is that open parenthesis, that parenthesis right there makes this thing an open interval. Whereas up here, we have a closed interval. And I think that pretty much explains this, doesn't it? Why doesn't it have a max or a min? Because it's an open interval. Fair enough? Okay. Next page. What made these weird? If you kind of go back to chapter 2, what word describes these two scenarios? Both of these graphs are what? Discontinuous. They have discontinuities in them. Okay? I think somebody asked about these two. What was the question on those two? What was it? Did you figure out what was it so we can all? What was the question, though? Yep. There's no absolute max. I got you. Right. So there's no absolute max because this one, we know there's points above that. Not directly in a line above it, but above it, right? There's points that are higher than it. Okay. So it's got no absolute max because that point right there, it's a quote unquote open interval there. Okay. So it approaches an undefined value. The key here is discontinuous. Okay. Because a discontinuity will cause a problem in a graph. Could there be a maximum value? Sure. But we just can't know for sure that there is going to be one if there's a discontinuity. If I had made this point filled in and this point open, that function would have an absolute maximum value. You see that? You see how I could change that up a little bit? If I made this one filled in, that's the absolute max. But as it stands, since that one's open, there is no absolute max. Good so far? Okay, so let's go back to this. Let's see if we we talked about this portion right here, right? Use page 248, right? Refer to that in your notes. Okay. Good so far. So, where do extreme values occur? Extreme values occur on a function at endpoints or at local max or min points. Okay? And we're going to do a definition here and kind of hone that a little bit. And I think the additional statement here that's important is where the derivative equals 0 or is undefined. We'll talk about that in just a moment. Okay. So extreme values are going to occur at polynomial graphs at nice smooth curves, maxes and mins, or at the endpoints. It also can occur where the derivative is undefined. I'll give you an example of that in a minute. Okay. 2 more new words, and I think that's mostly it for the new words today. Stationary point. A stationary point is a point at which it's a point C such that f prime of C is equal to 0. And the way I make sense of that is, remember going back to motion problems? Remember when we asked about places where the object was stopped or the object changed directions? Those were places where the derivative was 0, right? It's where the object was stationary, even for a moment. Remember the moving man when he went back and forth on the screen? In order to turn around, he had to be stationary for an instant in order to turn around and go the other way. Kinda? So they're stationary points where the derivative is 0. Singular points are places where f prime of C is undefined. Now that seems a little bit weird here, but there's a really nice classic example of a place where the derivative is undefined, where there is a minimum value, and that's on the absolute value graph. That is a singular point. We haven't defined it as such, but it is now a singular point because the derivative is undefined, but it also happens to be a minimum value for that function, for obvious reasons, right? Okay. Stationary points occur at smooth curves, max and min values. Okay? We can have a local max and we can have an absolute value. Absolute, not an absolute value, an absolute max. Okay? Endpoints, I mean, I don't know that this requires a lot of explanation other than the fact that if you're given a closed interval, they're going to be defined for you. They'll tell you that that function is on a closed interval. Okay. All right. We're going to get into the example in just a moment, but this is really important because this is the extreme value theorem. This is our first big theorem for this chapter, and it's one of them that gets tested in different ways on the exam on a very regular basis. So the two conditions, and when I ask about the two conditions, I would kind of refer back to page 248. What conditions had to be satisfied in order to guarantee that there's a max? I'll give them to you for now. The graph, first of all, had to be continuous. Those bottom two examples were great counterexamples for this, right? If the graph is discontinuous, there's not necessarily a max or a min. There could be, but there's not necessarily a max or a min. And the second qualification is that it has to be on a closed interval. Okay, those empty circles or the parabola that continued forever are good counterexamples of that. But here's what you know at this point, or what you should know at this point. If a graph is continuous and it's defined on a closed interval, you are guaranteed a max value and a min value. That's the extreme value theorem, and it is on page 249. Look at it quickly. It doesn't look like it says a lot. Just open to page 249 and read it to yourself really quick. Not a lot of words there, right? Pretty simple idea. If the graph's continuous and it's on a closed interval, guaranteed there's a max and there's a min. Okay? Here's how we apply it. You ready for this? Ready for the actual example? Enough vocab and theory? I'm going to ask you to jump to the back of your notes because the example I'm going to do is a little bit easier than the one that's there on your notes. So I want you to go to the back page, and I'd like you to outline this problem. And we can talk about the one that's in your notes a little bit later, but it's got rational exponents, which make it a little bit more difficult to see at this point. We can talk about it another time, but I want to put this in a context that makes more sense right now. So will you write down this equation on this interval? F of x equals 4x minus x squared plus 6 on the interval from 0 to 4. Write that down on the back page of day 1 notes. There's space back there, right? I had intended to do that nasty rational exponent problem, but I figured with all the vocab we did, you might get a little bit annoyed by the fact that we're doing a really hard problem, the first example for this. Okay? All right. As you outline this problem, I'd like you to write the letter A and write the word continuous with a question mark. And in a moment, we're going to answer that question. Think back to chapter 2 on continuity. Remember the formal definition for continuity? You're not a bad person if you don't remember it right now. There were 3 things. What was the first thing? The limit was the second one. The first one was f of a exists, so the point exists. The second one was the limit exists. And the third one was the limit equals the function, right? That was continuity. Now, we talked later that there was a simpler definition of not really definition, but there was a simpler way we could think in terms of continuity. If we know something about the function, can we determine continuity? Look at the equation, and I want you to answer the question. Is it continuous? Yes. How do you know? Because it's a parabola, and polynomials, aka parabolas, polynomials are always continuous on their domain. So is it continuous? Of course it is. Okay? It's a polynomial. It's a parabola. And parabolas are continuous. There's no jumps or holes. Okay? Now, second question. Is it defined on a closed interval? Yes, it is. What is the closed interval? It starts at x equals 0, and it goes to x equals 4. And I've got square brackets around them. That's implication of closed interval. If one of those was a parenthesis, would it be a closed interval? No. Only because these two things are satisfied, we are now guaranteed what? A question, or do you know the answer? What is the answer? Because these two are satisfied. Okay. Because these two things are satisfied, what do we know? There's a max and there's a min, guaranteed. Okay? Doesn't seem that profound, but they're going to find little ways to test that, and we'll get to one of those here in a little bit. Okay? So now the question is, if those two criteria are satisfied, here's our question next. How do we find the max and the min. Okay? And I think one of the last things we did before we got to this example was we said that if a max and a min is going to occur, it's going to occur where? At a critical point or an endpoint. Okay? It's going to occur at a critical point or an endpoint. The bummer is we don't have our graphing calculators. I think we know something about this function, but we need to be able to defend which point's the biggest and which point's the smallest without actually seeing them on the graph. How do we do that? We plug stuff in. We find out how big the endpoints are. Fair? And then we find out how big the critical points are. Okay? So let's do this. Remember critical points? F prime is 0 or F prime is undefined. In order to determine if F prime is 0 or undefined, what do we need to do first? Find F prime. What is F prime? It's 4x minus x squared plus 6, right? F is 4x minus x squared plus 6. So what's F prime? 4 minus 2x. Be careful. Wait for the whole question before you answer it. Is there a place where F prime is undefined? No. It's defined everywhere. Why? Because it's a line. Lines are defined everywhere. Is there a place where F prime is 0? Yeah, what is it? 2. We say 4 minus 2x equals 0. We solve for x by adding 2x to both sides. We get x equals 2. What do we call that point? I think I heard it. It's a critical point. More specifically, it is a stationary point. Okay? Here's an idea that I'd like you to consider when you're doing these. Okay? This is really important. And I like this word in this context. Because there are candidates. We know there's a max, we know there's a min. Why? Because of the theorem. The max might occur at a critical value, it might occur at an endpoint. Same with the min. So I like to write this. The candidates for this would be endpoint, f of 0, endpoint, f of 4. That's an endpoint, that's an endpoint. What's the other candidate for a max or a min? 2. Why 2? It's a stationary point or a critical point. You could call it a critical point if you'd like. Okay? Now, at the beginning of the hour, we looked at a graph and we said, how do we know it's the absolute max? And you said, duh, it's bigger than all the others. Unfortunately, we don't have a graph. This is a pretty simple function, so I think you can get it. But if we don't have a graph, how do we know which point is the biggest? You can answer. How do we know which point's the biggest? Plug it in. It has the biggest y coordinate, right? So what is, based on that original equation, what is f of 0? It's 4 times 0 minus 0 plus 6, so that's 6, right? Is that the biggest? I don't know. Let's try the other ones. We have to try the other ones. Seems ridiculous and a little redundant, but you have to try all of them in order to determine which one's the biggest. Let's try f of 2. F of 2 is 4 times 2 minus 2 squared plus 6. 8 minus 4 is 2, 4. 4 plus 6 is 10. Is 6 the max? Sure isn't. Why? Because 10's bigger. Okay? I know I don't want to oversimplify it, but I also want to make sure that I hit it in full detail. F of 4. Well, that's 16 minus 16 plus 6, aka 6. What's the max? 10 is the max. Think about this for a second. I don't want you to think about it for a long time, but I want you to think about the fact that how can we be sure that there's not a point bigger than 10? The other two sides are 6, and we found all of the critical points. There's no other critical points on this curve. There's no other places where the graph could turn, right? It only turns once. It's at 6, it's at 10, it's at 6. It can't turn again, right? Why? Because it's a parabola, right? We knew this. So what's the minimum value? 6 and 6. It happens to occur twice. Not a big deal. That happens all the time. Okay? So the maximum value of the function is 10. Notice it did not use the word absolute. It doesn't need to. The maximum value of this function is 10. The minimum value of the function is 6. Note, did not use the word absolute. It's implied. Okay? Fair? I don't want to spend a ton of time on the local extreme point theorem. I think it speaks for itself, and we're going to do one example just in a minute to kind of prove the counter of this. I'm not wild about this question right now, but if f has a local max or a min, and the derivative exists, if there's a max or a min and the derivative exists, that derivative was 0. It's kind of self-explanatory, isn't it? If there's a max and the derivative exists, the derivative value had to be 0. Is that fair? Okay. This is kind of a, I don't want to say counterexample. This is an old multiple choice question from an AP exam, and it almost applies with the extreme value theorem. We'll walk through this really quickly. Will you read that question? I underlined a couple things that are really important based on what we talked about today. Does it make sense that I underlined them? It's continuous and it's on a closed interval. So what do we know? There's a max and a min. But it's not how you would expect, because if you keep reading, there is no c on the interval such that the derivative is 0, which means there are no critical is not the right word here. There are no stationary points. You're really close with critical, but that distinction is going to be really important. There are no stationary points, meaning there isn't one of these and there isn't one of these. We know this. F of -2 is 0. F of 2 is 0. Oh, man. Are you picturing a horizontal line segment? Aren't you just picturing this? No? It can't be that. Why not? Because it says there's no C that has a horizontal tangent. Let's go through the multiple choice answers. Which of the following must be true? Okay, part A. Does the derivative have to be greater than 0? Does that have to be true? Does the function have to be increasing? It doesn't have to be. It doesn't have to be true. Does the function have to be falling? F prime less than 0. Does it have to be falling? It doesn't have to be. Does the derivative have to exist? Remember differentiability? Remember what conditions functions were not differentiable? It was a two-word phrase. Functions are not differentiable if there is a sharp corner. That's the phrase. Could there be a sharp corner here? Sure could be. Does the derivative have to exist? I don't think so. For the function, the derivative exists, but it's not continuous. We don't know anything about the continuity of f prime. Don't pretend you do. We don't know anything about the continuity of f prime. That's just a weird thing to think about. The only one that makes sense here is this one. There has to be some value for which the derivative does not exist, i.e., there has to be some sort of sharp corner. Because I don't know for sure which of these two scenarios is true, but one of these two scenarios has to be true. The function has to rise and then fall. How else would it get from one of those points to the other without coming back down, right? Because it says the function's continuous. Or it has to fall and then rise. But you notice I made sharp corners. Why did I make sharp corners? There can't be a smooth curve because it told me the derivative is never zero. Okay, let's wrap up. We did vocab with critical points. We did vocab with stationary points. We talked about the max and min existence theorem. If those two conditions apply, if it's continuous and it's on a closed interval, there has to be a max and a min. How do you find the max and the min? You check the endpoints, you check the critical points. One of those things has to be your max and min. Questions so far? This is what I would like you to work on. First thing tomorrow, we'll get those last related rates quizzes back.